Chapter 23, Computational Chemistry. Section 23.1, Potential Energy Surfaces. A potential energy surface shows how the potential energy of the molecule changes with the atomic positions. Here, the potential energy of the molecule is defined to be the total energy of the molecule minus the kinetic energy of the nuclei. Accurate potential energy surfaces are useful in the study of chemicals and reactions. The X, Y, Z Cartesian coordinates are rarely used when plotting the potential energy surfaces. Instead, the internal coordinates, such as the interatomic distances, bond angles, and dihedral angles, can better illustrate the relative positions of the atoms, and therefore are typically used in the potential energy surfaces. For example, the potential energy surface of a typical diatomic molecule is shown here. The vertical axis is the potential energy. The horizontal axis is the distance between the two nuclei. And now we have two different potential energy surfaces in green and blue. The green one is assuming the harmonic oscillator model. The blue one is much more realistic. This is Morse potential. And over here we can see the dissociation energy at the line, this dashed line. And we have D sub E, the depth of the potential energy well, D sub 0 as the bond energy. The Morse potential can be written as a mathematical equation. The potential energy is equal to D sub E, the depth of the potential energy well, multiplied by 1 minus e to the power of negative ax squared. So you can see this x is the displacement of the bond length. When x is 0, that means we have equilibrium bond distance. And then we have 1 minus 1 squared, it's 0. The potential energy is 0 when the displacement is 0. What if x is infinity? When x is infinity, we have this part equal to 0, and then the potential energy is equal to D sub E. Again, this is the simplest potential energy surface because we have the potential energy with respect to just one variable. When you have a diatomic molecule, you just need the distance between the two nuclei to specify the relative positions of these two atoms. Now we're looking at a more complex potential energy surface. When we have a nonlinear molecule, there are 3n minus 6 internal coordinates. Because we have 3n different motions, minus 3 translation, minus 3 rotation, and then we have 3n minus 6 internal coordinates. If we have a linear molecule, we have 3n minus 5 internal coordinates because there are 3 translation and only 2 rotation of the molecule. It's often impossible to plot the potential energy surface versus all internal coordinates. For example, if you just have water, 9 atoms, there are 3 internal coordinates. There's OH bond and the second OH bond, and then there's HOH bond angle. And how can you draw a potential energy surface that depends on all 3 variables? Bond distance 1, bond distance 2, and then bond angle. So we often just plot the potential energy versus only one of the many internal coordinates. We pick the most important one, the one of interest. For example, if we are looking at the rotation of the carbon-carbon bond in a butane molecule, we usually just look at the CC-CC dihedral angle. So why 4 carbons here? To define a dihedral angle, we need 4 atoms. It's going to be atom 1, atom 2, atom 3 behind this, and then atom 4. Really, atoms 1, 2, 3 can define a plant. Atoms 2, 3, 4 can define a second plant. So the angle between the first plant that contains atoms 1, 2, 3 and the plant that contains atoms 2, 3, 4, that angle is the so-called dihedral angle. So again, if you have a butane molecule, we have 4 carbon atoms. Carbon 1, 2, 3 can define a plant. Carbons 2, 3, 4 can define another plant. The angle between the two plants is the CCCC dihedral angle. So now let's look at this potential energy. So right here, I think we have the lowest energy when this dihedral angle is 180. Well, this is simply just because if you look at this methyl group and this methyl group, the one is pointing up, one is pointing down. We avoided the steric hindrance between the two methyl group. That's why it has the lowest energy. Now over here at this point, we have the highest potential energy. Look at the positions of these two methyl groups. They are much closer to each other, and same here. That's why we have a high potential energy at this 2 point. Now what about this two so-called local maxima? Over here you can see there's a smaller steric hindrance between a methyl and hydrogen here, methyl and hydrogen here, smaller, much smaller than between two methyl groups, but still you see the two local maxima here and here. Now let's look at two other values. When you look at these two other values, they are both staggered conformation. So there's not much steric hindrance, but still these two methyl groups, they are still fairly close to each other. All right, compare with this. This two, the dihedral angle is 60 here. Over here, this is 300, which is actually 60. And compared to the middle one, you can see these two methyl groups are still closer to each other than this in this configuration, in which these two methyl groups are pointing to completely opposite directions. So now we looked at this so-called global minimum, and then two local minima, and then the global maxima and some local maxima, and then we can connect those and draw the potential energy surface for the rotation of the carbon single bond in the middle. Again, the energy goes up and down mostly due to the steric hindrance. It's possible to draw a three-dimensional plot of potential energy versus two coordinates. It's a little hard, but it's possible. So for example, when we have water, there are three internal coordinates. If we force the two OH bonds to have the same bond distance, then there are still two internal coordinates. One is the bond distance, the other is bond angle. So again, the vertical axis is the potential energy, and then we have two other axes. One is the bond distance, the other is bond angle. And we're just examining this curvy potential energy plan over here, and somewhere we have the lowest point on the surface, and the lowest point corresponds to the equilibrium bond distance 0.096 nanometer or 0.96 angstrom between the oxygen and the hydrogen atom. And then we have a bond angle roughly 105 degrees. That's the equilibrium bond angle in water. And then you can just change its bond distance, longer or shorter, and it goes up. Also, you can start from here and change the bond angle. You can make the angle wider or narrower. Also, energy goes up. So this is a three-dimensional plot of the potential energy surface for water when we assume the two OH bonds have the same bond distance. Now let's look at another potential energy surface of a triatomic molecule. This time we're looking at ozone. Again, we're going to have to assume the two O bonds have the same length so that we can make a three-dimensional plot. Otherwise, we are looking at a four-dimensional plot. So by having the two oxygen-oxygen bond distance to be equal to each other, we have only two variables. One is the bond distance, one is the bond angle. So we have bond distance right here and bond angle over here from 50 to 130 degrees. The bond distance is from, I think, 1.1 angstrom all the way to 1.5 angstrom. And you can see this potential energy surface here. The vertical axis is energy in atomic units. One atomic unit is 2,600 kilojoule per mole. So actually there's a large difference between here and here. They differ by 0.7 atomic unit, and 0.7 atomic unit is nearly 2,000 kilojoule per mole. Huge energy difference. So this is one of the input files for doing Gaussian calculation. Gaussian is a computational chemistry package. You can use it to do some calculations. So in the first line, I just specify the method I'm using. Scan means to scan the potential energy surface. And a blank line, a comment, another blank line. 0 means the charge of this molecule is 0, and 1 means the spin state is singlet. 1 stands for singlet, 2 for doublet, and 3 for triplet. And I have 3 oxygen atoms, so 1, 2, 3, 3 rows, 3 atoms. The second oxygen has a distance from the first atom. Alright, this means the first atom. The distance is r. The third oxygen also has a distance from the first atom. Also, the distance is r. So I'm just forcing this two to be the same. And then there's a bond angle. I'm using a name theta here, and then r is from 1.1 to 1.5. So really, we are gonna do 40 increments. Each is 0.01 angstrom. So it's gonna be from 1.1 to 1.5. with the increment of 0.01 at a time, and theta is from 50 degrees to 130 degrees. So again, we're doing 40 increments here. Each increment is 2 degrees, so we're gonna do 50 plus 80 degrees. In the end, that's 130. Just to summarize, I'm gonna just compute the energy of ozone when the bond distance is between 1.1 to 1.5, when theta is between 50 to 130. So really, we need to do more than 1,600 energy calculations, because when you look at the values of R, we can have 41 possible values. All right, this is the first one, and then 40 different other values. Also, for bond angle, the first bond angle is going to be 50, and then we're going to do 52, 54, 56, 58, etc., all the way to 130. So since we have 41 possible values for R, 41 possible values for theta, we do have 1,681 data points on this potential energy surface. So this is why the calculation of the potential energy surface often takes a very long time. From this potential energy surface, we can identify the minimum. I think the minimum is somewhere, the global minimum is somewhere here. The bond angle is probably 115 degrees. It's a little hard for me to visualize the three-dimensional plot, and also the bond distance. Again, the bond distance is hard to kind of, so it's roughly here. I'm going to draw a line here, roughly 1.25. I'm just estimating this, but if you really do the calculation, you will be able to get the energy value for every single data point on this potential energy surface.